Okay, welcome everyone. This is the week 10 webinar. In fact, it's our second to last webinar of the quarter. So next week will be our last one. Hopefully you know what second to last means. And a lot of what's on the agenda, you probably have no idea what it means. Some you do. I hope number one you all do, and that is Q&A. So I'll always answer questions if you have them. Just let you know, there's a chance that today I'll go a little shorter like last week. We'll see, depends on questions and all that kind of stuff, because we're doing chapter 12 today. So we'll talk about scatter plots and what they mean. Then we'll look at R, and that is the correlation. You've probably all heard the word correlation. My guess is you don't know how to compute the correlation by hand if you needed to. Okay, and I would tell you, even if you did know, you wouldn't want to. But there is a correlation, and we'll talk about the correlation between two things. And then this looks really easy. You know, if you know R, then R squared. And actually, it's very easy to find R squared once you know R. But the interpretation of R squared actually is very deep. So we'll talk about that. And then we'll get into the equation of the regression line. So we're going to be looking at regression analysis today. That's what chapter 12 is. And it has an equation. It's a line. And hopefully you remember from some time, not in this class, that when you're looking at a line, it has a slope and it has a y-intercept. So we'll talk about that slope and that y-intercept and how to interpret it and use it. Okay, each of them. Okay, and then I can't say this often enough, avoid causation. Okay, and that's pretty much for this entire course, but regression analysis is where people really make that mistake. So never ever have any verbiage that kind of even hints about causation when in this chapter. That's just a big no-no. And then, since I promised that every chapter is going to have hypothesis tests, hypothesis test for, who knows what this letter is? Here's a hint, row, row, row your boat. This is the letter rho. So it's the letter rho, and rho is, you may or may not know, is the Greek letter for R. So R will be the correlation from the data. Rho will be the correlation for the population. So that's what we're going to be looking at. Okay, and you can only get a hypothesis test. You can't get the whole population in most cases. So that's what we're looking at. So that is the plan today. I do want to remind you about kind of the next big thing coming in. I mean, you still got a little bit of time, almost, you know, more than a week and a half, but not too much more. And what is that? Yeah, project 2. So make sure that you have made progress on project 2. Post on the project 2 discussion board your idea, your plan, and I'll let you know if it's going to work. And if it is, I'll tell you. I mean, if it isn't, then I'll give you either some suggestions on how to tweak it a little bit to make it work, or I'll let you know, come up with something else, you know, depending on, you know, what you've written. So project 2 is important, and hopefully you all have project partners. So those who have been like not having one, I've been doing a lot of matchmaking and, you know, helping you out, but hopefully everyone's got project partners now. Same rules before, 3 people or 2 people. 3 is better than 2 because you have less work to do. And also if someone drops and you still have 2 left. Okay, so anyhow, that's the big plan. And the other thing is, this is week 10. 10 is a multiple of 2, which means?
An exam.
Yep. there's an exam. So you're going to have week 10 exam. So, be ready for that. And that will, be this week. Get an hour and a half. And unless you have a disability that needs accommodations, and then there could be addition, but for most people, it's an hour and a half. And just like before, all the rules are the same. And same idea is that the first half or so will be on the older stuff, but now there's more and more older stuff. So, it'll be weeks, chapters 1 through 10 is that 50%. And then 11 and 12 will be the other 50%. And the written questions will be, or the typed out questions, I guess I should say, will be the chapters 11 and 12. So that's just a note. So that's the plan. Any questions at all about the plan today or about anything else? It's a great time to ask. Any questions? Okay, if there aren't questions, I'm going to go over what I consider the most important regression analysis and statistic, actually, that has ever been done in my area, which is Lake Tahoe, by the way. Any guess? And it's not something like personal about my daughter important or anything like that. This is important for my area. Snow's important, but let's just put it this way. It's only this area. It wouldn't be, say, Mammoth. And Mammoth has more snow. Yeah, lake. What about our lake?
Probably the clarity or cleanliness of it.
The clarity. So I don't know if y'all know, but there is a lot of work. And again, if you're not from Tahoe, if you've never been to Tahoe, please come because it's so beautiful, not because of this class, but it is one of the prettiest places on earth. But we want to keep our lake beautiful. And one of the great things about the lake is that it has great clarity. So it's this beautiful blue lake. And so every year what they do is they measure the clarity. And that's interesting. And by the way, who's the they? Anyone know? This is kind of interesting.
Scientists?
Yeah, which scientists then, specifically?
I don't know.
UC Davis. So University of California, Davis. So UC Davis, they're the ones that have the whole scientific piece of that. And they do all the measurements. And let me show you. Actually, I'll show you in a little bit. First, I got to talk a little bit more in general first. Do I have that? Not yet. Okay. I think I want to jump. Well, I think I put this in a weird order. This is the data and the study that was done by the UC Davis researchers. Okay, and you could trust them. They're not going to make more money by cheating or something, so there's no reason to. And they collected this data, and they did. It's called the depth of clarity, how far you can see down. And they do. They use what's called a Siki dish. Basically, it's a little white plate. They put it on a big rope. They slowly let it go down until you can't see it anymore. And then they measure how far it went. And that's the clarity. And the cool thing is when they had a little, I don't remember where it was, but they had a booth one day, and I was able to come up and talk to them. And I asked him, well, when you measure the clarity, what do you do? Because, different times of the years are different, and, all kinds of things. And they said, oh, well, we don't just do one measurement a year, we do many. And I asked them how many, and what they said made me smile. Any guess? This is what the guy told me. Not every day. That'd be good. But this made me smile because of what I teach. Should I tell you? 31. They said they measured it 31 times that year because they wanted to make sure that they take the average depth of clarity and you have a normal distribution for the sampling distribution. And that's really important. And you do kind of have to have that to do this analysis, to do it right. You know, and these are scientists at UC Davis. They're going to do it right. They understand statistics. That's the good news. So what they do is they measure the clarity. And this is there's a picture that they post on their website. And I copied and pasted a piece of it, because what I had is I had a student, actually. I've been teaching a long time at the, I think it was around 2000, just around here, who came to the big meeting. And it was a meeting with politicians, including the most important politician there was in the whole world at the time. Anyone know who that was? I know you got no history. It was President Clinton. Yeah, so it was President Clinton, and he, unfortunately, he understood statistics. I think that, to me, that should be a requirement of every president we ever have, is they should understand statistics so they can get what's going on. They should take this class. Okay, it doesn't have to be with me, but you know. So they showed this to the president, and not just the president, but there were a lot of other important politicians there. But the president, of course, is the most important, and our governor and some senators, etc. And you look at this, and do you see a trend, just kind of visually? Okay, so just a note, this is called a scatter plot. So this is called a scatter plot. And that means that you have two variables that are both quantitative. And for every year or whatever you're looking at, could be every person, but in this case, it's every year, then there's going to be a year and there's going to be a measurement in this case. Sometimes it could be two things that are quantitative, but they may not be year and measurement. They could be something else. Okay, but in this case, they're year and measurement. So when you have two quantitative variables, you can graph them as points on a graph. Okay, so for example, this point right here looks like 81, comma, maybe 28 is this little dish. Any questions on that? And when you graph all those points from the two quantitative variables, that graph is called a scatter plot. Okay, so that's a big word, an important one. Just a note, and I want to let you know, I'm not the one that created this graph. But if you can imagine a line, which they kind of mostly drew, that goes through here, then you can think about the line, and you can think about its slope and its y-intercept. Here's a trick question. Is the slope of the line positive or negative, this line? What do you think?
Either?
Definitely not neither. Okay, and the hint was, it's a trick question. It should feel like a positive slope line because it goes up as you move, right? But it's a trick question if you look at the y-axis, because the y-axis is upside down. Because they wanted to make it look like depth. So this actually has a negatively sloped line. As you go from left to right, it actually goes down because you go from like 30 to like 20. Do you see? As you move from left to right. I wouldn't do trick questions like that, but I'd like to give you the most important real life example that's ever happened in Tahoe in statistics, at least in my feeling. And that is this. Okay, So basically we see that as time goes on, the depth of clarity has decreased. Do you see? Because we've gone from over 30 to under 25. Do you see? Okay, doesn't sound like that much, but these are meters. Okay, so that's like 15 feet of difference in how far deep you can see. That's a lot. That's a big difference. If you were around, I guess I was a baby around here, but I wasn't in Tahoe, and you could really see a lot farther than now, than this year. Okay. Any questions so far? Okay, the other thing we want to look at is if you look at these data points, they're not all on a perfect line. Do you all agree? But can you, if you weren't given this line, can you visualize a line that would kind of follow the points pretty well, even though if it's not perfect? Okay, and if you can, then we say that there's a good strong correlation, especially if you can easily visualize it. Okay, if the points are just all over the place, and of course you haven't been able to see this for a long time, but if you looked up in the sky at night, you could see stars. Unfortunately, that's not true anymore, but eventually we'll be back. And if you look at the night sky and you look at the stars, do you see how, like, do they lie like on a nice kind of line that you can feel, or are they just all over the place? If you look at the stars in the sky, yeah, they're scattered. And when you're all scattered, then you have a near zero correlation. Okay, and if the slope is positive, then the correlation is positive. If slope is negative, the correlation is negative. If slope is zero, then you have zero correlation. Okay, or if they're all scattered, you have zero correlation or close to zero. Any questions on that idea? So I'm kind of going through ideas first before we actually get all the numbers from this example, which we'll get in a minute or two. Okay, so we have this correlation, and it's important because if the points, if the variables are not correlated, then regression analysis is useless. Just let you know that. If they are correlated, then you want to do regression analysis, because regression analysis tells you to predict, in this case, the number of meters given a year. Even if the year is not exactly here, let's say it was 2005 over here somewhere. Well, we can predict it, and you probably wouldn't say it would be 30 meters, would you, in 2005? What would your prediction be just by looking at this? Any guess? If you looked at 2005, what would your prediction be for the number of meters just by visually looking?
Somewhere between 15 and 20, I would guess.
Yeah, maybe between 15 and 20, which is awful, by the way. Okay, but that's what you would predict. Do you see that? So having a strong correlation and doing those statistics will help you predict the future. Okay, and many other things too, right? In this case, the future is what you're most interested in. Okay, any questions on this? So as I mentioned, what happened is the President of the United States, along with many other important people, were in Tahoe, and they were given a presentation, and they were shown this picture. Okay, and we'll talk in a little bit what they did, but I'm going to show you more than just this picture. We're going to actually look at the numerical statistics that we can do instead of just saying, yeah, we got a correlation, or it's a negative correlation because it's a negative slope, even though it doesn't look like it. Do you see that? But we'll actually have a lot more than that. Any questions so far? Any questions on that? Okay, so what we can do, and I forgot to do this ahead of time, so sorry. Let me go to it. Just takes about 10 seconds. to get to the calculator. And where is that? Oh, I think I'm in the wrong one. It'll be easier to be section 1. It's easier to find the calculator, I think, quickly. It's on page 1. There we go. Okay, so we can go to the calculator. And take a look. What calculator number do you think we're going to use?
24.
Okay. And by the way, we are almost done with this course. As I said, this is our second to last webinar. Guess which calculator number we're going to use next week?
25.
Yep, it should be obvious. So we're on regression analysis. And I let you know, it's a pretty deep subject, but there's only one calculator. We're not used to that. We're used to many calculators. But for this week, it'll be regression analysis, period. That's the calculator. So I can click regression analysis. And something I did, there's two ways of doing it. One is you can plot the point one point at a time, but I realize that's a pain in the butt when you have a big long list of points. So I also made it, you can put in all the X's and all the Y's. The ordering is important, by the way. If you switch around the ordering, it's just wrong. So you have to keep the ordering as how it was. So this is completely dependent data is the idea. Okay, so let us go ahead and I'm going to copy and paste. First thing, the X's, which are a little bit boring, 68, 69, 70, 71, 72, 73, all the way up to 99. Because that's what they knew when President Clinton came. And then I'm going to pop it in to the X's. Any questions on that? Notice they're separated by commas. And then I'm going to take these numbers. These numbers, by the way, I had to actually get from them because all they had was this picture. So I emailed them and asked them for the actual data and they gave it to me. So, you know, good thing is university people are usually pretty nice. They'll give you stuff like that. So let's put them in. And then I just click plot points. And unlike UC Davis, I actually made it more mathy than picturesque. You don't see Lake Tahoe with a boat, which means that you're actually getting a negative sloped line, which is what it should look like, right? But you don't see that pretty lake with the boat. You just see a bunch of dots with the line. Okay, any questions so far? Okay, I also, when I programmed this, when I coded this up, you'll notice that right here is not the origin. This left, bottom left, the origin doesn't even show because the origin's not really part of the focus of any of these points. Okay, and in fact, the way I've created these numbers, 0 would correspond to the year 1900. And in those days, and way before, you know, way after that, actually, no one was even thinking about measuring lake clarity. Okay, really, it started in 1968, was the first year that they measured lake clarity of Tahoe. So that's just a note. And similarly, it would really suck if our lake clarity went to 0, wouldn't it? So this actually starts at kind of the lowest values you get, or close to the lowest values. That's kind of how I set this up. Any questions so far? Okay, so this is a scatter plot, and now we really can see the regression line as it should look. And that is this negatively sloped line. Any questions on in viewing this guy? Okay, so I'm kind of doing this in general first, and then we'll get into actually full interpretations. Okay, then in here in the what I put in is the regression equation. And the regression equation is y equals 48.2765. And it says plus negative 0.2804x. It turns out I made it this way because it's more convenient to do a plus negative than a minus, because it's the slope that we're interested in. And it's easier to read the slope if it's written this way. The number of decimals really all depends on what you need. Most of the time, you won't really need 4 decimals, but that's what this gives. Okay, so that's our y-intercept. And hopefully you remember, what number is the y-intercept in this example? When we see this equation, how do we find the y-intercept? It's supposed to be easy. It's not a trick question. Anyone, any ideas? Give you a minute. It's actually very important to be able to, read it off. I don't see y'all jumping in. Okay, I'm looking for a number though. I see an equation, and x plus b is not quite it. You might have forgotten something. But what's the y-intercept? What number is the y-intercept?
I'm just gonna guess 0, maybe.
No, good try though.
1.
No, it's 48.2765.
That
Right?
makes sense.
Because if x is 0, y is 48.2765. And that's what y-intercept means. It's when x is 0, what is y? Any questions on that? Okay. And the slope, what's the slope? Also very easy to read. That's a hint. Big hint. It's pretty hard to get this one wrong.
The negative 0.2804.
Yeah, so negative 0.2804 is a slope. Okay, and I know this sounds weird because you're used to mx plus b. There's a reason, which I can't get into, that you write it this way instead, is y-intercept plus slope times x. And everyone writes it that way, but there's a reason that is difficult. I'll stop there. And I'll let you know that this regression analysis stuff can get much more advanced. So what this is the equation of the regression line. It turns out you can do a parabola or a circle. You can do all kinds of different curves. And you can do regression for anything. This class, elementary statistics, we stick with lines. So that makes it easy, by the way. So it's always going to be a y-intercept and a slope. Any questions on that? The other thing I want to give you a heads up on, which people make a mistake, especially on the discussion post assignments, is that there's another type of regression analysis that people do that's much more advanced than this, and that is a multiple regression analysis, where you have more than one variable. And that comes up a lot, especially in research. So when you're looking online and finding, regression analysis stuff, make sure you don't do multiple regression analysis. Make sure you're doing just one independent variable. And I can't get into anything about more than one independent variable other than it comes up a lot in the advanced world, but not in elementary statistics. So when you go in and look at, different articles for your discussion post assignment, make sure that it's a single variable regression analysis. Okay. So make sure that you can see and come up with, if you can't come up with this equation, like by looking at their picture that had a line that might look like mine, then it won't work for your post. Okay, so that's a big suggestion I have, is that when you're going to make your post, make sure that you can write down the equation of the line. And if people can't do that, then it won't work. Yeah, it's also called multilinear, multiple. There's a lot of words for it, but the most important thing is make sure that you just get a single equation of a line or a picture that looks like this. Okay. Any questions on that? Okay, R stands for, and correlation. And I think they use the letter R. I'm not sure, but I think they use it because it's the first letter of regression. It's too bad it should be C, but I don't get to pick the letters. Everyone in the world uses R. So R is a correlation. Notice that it's a negative correlation, which it better be because the slope is negative. It's also pretty close to -1. So it's on the negative, it's far away from 0. You can't get less than -1 and you can't get greater than 1 for correlation ever. So correlation is always between -1 and 1. So if you're close to -1 or you're close to 1, then you have a strong correlation. Okay, and here we have a strong negative correlation. R squared, I'll usually round to 2 decimals, so 0.84. Okay, and that most people call R squared. That's what they call it. You don't hear words for it, actually. You just hear R squared, but R squared is really important. And everyone, all people who know statistics know what R squared is. Okay, and in a little bit, I'll talk about how to interpret R squared. Okay, and then we're going to have a hypothesis test. Most of the time in our class, it's going to be two-tailed. Because if we want to see, is there a correlation? And if we want to find out, is there a correlation between year and depth of clarity, then it's going to be two-tailed with a not equal sign. If instead you want to hypothesize there's a negative correlation, then you choose this one. Rho, remember that letter is rho. Rho is less than 0 for HA. And if you want to show it's a positive correlation, then you're going to say rho is greater than 0 for HA. Okay, and for HA. H naught will always be rho equals 0, by the way. Okay, that's always. Any questions on that? Okay, it turns out, and this is very difficult, which is good for you guys. If it's very difficult, what does that mean?
There's usually a calculator for it.
Oh, even better than that in this case.
We don't have to do it at all.
You don't have to know and understand any of it.
Yeah.
But it uses the T statistic, the same statistic as the statistic we use for measuring a difference between two means or measuring a single mean population mean. A hypothesis test for a mean. Remember that T? So it uses the same one. The reason why we're not going there. Got it? Okay. And the calculator will just give it to you. And hopefully you all know how to look at the word p-value and be able to say what the p-value is. And I want to give you a reminder. Is the p-value approximately 2.56? What do you think?
No.
No, the p-value can never be bigger than 1. What did I miss out talking about? If all you look at this, you'll never get it. Yeah, we have that E -13. That means we need to move that decimal 13 places to the left. You can have 12 zeros before the 2. So that's like pretty much as strong evidence for statistical significance as it gets. Is that clear? Because that's as close to 0 as you'll basically see. So that means that we get to reject the null hypothesis. And that means there's a correlation. And again, the good news was the president of the United States understood what that meant. And I will let you know, not all of our presidents have understood statistics. It's a bit sad sometimes, and I'm not going to get into politics, but I do want all presidents to know statistics, and I think I can get away with saying that. Okay, so there's our p-value, and that tells us there's a correlation. It does not tell us that the correlation is strong. It just tells us that we have a correlation and that we have strong evidence that there is a correlation, but that correlation could be weak. So know the difference between strong evidence that there's a correlation and having a strong correlation. Do you see that? You can have strong evidence for a correlation because you have a very big sample size, even if the correlation is weak. Because remember, if you have a very big sample size, the truth will show up in a strong way. Do you see that? So if you have weak correlation and you have a giant sample size, you're going to have very strong evidence that there's that correlation, even though it might be 0.01 for the correlation. If you had a million sample size, you're going to have a tiny, tiny p-value. Do you see? So that's just a note, and so don't get confused between those two things. Okay. But the R tells you the correlation's strong because the R is close to -1. So that tells us this correlation is strong. So we actually have strong evidence for a correlation. And then the R will tell us that the correlation is strong, and it's strong negative. It's negative, strong negative correlation. Any questions on kind of reading all of these pieces of this calculator? Any questions on this? Okay, so now I'm going to, now that I went over this stuff, now let's get into words and like really talk about, what you can say specifically about all this stuff. Now that we've seen all these numbers and maybe kind of understand them. Any questions so far? Okay, so let's put them in here. We already decided the slope was, where was it? About -0.28. That's good enough. That's enough decimals that anyone would care about, because no one really cares that much about 100th of a meter for clarity, because your eyes probably can't even tell, that well. And by the way, that 100th of a meter is you should all know this actually. It's a centimeter. Well, maybe you don't know it. Yeah. So you should all know about 100th of a meter. So I'm going to go to 1 centimeter. I don't care about a millimeter of clarity. So -0.28 is our slope. All right. Now, hopefully you remember from school that the slope is a rise over run. Do you remember learning that once? That's by definite. That's what you learn in math, right? The slope is rise over run. So I'm actually going to write that down. Okay, just to remind you. So we don't have a fraction, and you usually won't when you use a computer. So for any number, there's always a way to make it a fraction. And that is write it over 1. Okay, so hopefully you know that -0.28 is the same as -0.28 divided by 1. Any questions on that? I know that's really silly math, but it turns out it's going to be very helpful for understanding how to interpret these things. So the rise is the numerator, which will be -0.28. The run is the denominator, which is 1. Any questions on that? Okay, so now let's interpret the slope given what we've got here. Okay, so that says that if you run by 1, your best guess is that you're going to rise by negative 0.28. Any questions on that? That's what slope means. Okay, well, running by 1, the run is the change in which variable? When you rise or run, the denominator or the run is a change in what variable? Maybe I'll start with rise because that might be easier for you. The rise is a change in what variable? If you rise, are you changing by, is X changing or Y changing if you're rising?
Is it Y?
Yeah, Y is changing, right? And in
Yeah.
particular, Y is meters of clarity, right? Okay, and run will be the change in the X variable. When you run horizontally, right? That's why they call it rise or run, by the way. That's the reason for those words. Okay, so you're going to run horizontally, right? So in this case, these numbers are years, right? They're actually years since 1900, the way I wrote it, just so there's less typing. Otherwise, it's just too messy on the graph. Okay, and actually not me, I didn't write this one, they wrote it. Yeah, they put these numbers in. Okay, so notice the rise, this means losing 0.28 meters of light clarity. Do you see that? Because negative means you're going down. That's bad, right? Losing clarity. The run, that means we're going up by 1 year. So 1 year has passed. Any questions on that? All right, so now I can interpret the slope. So let's interpret the slope. What it says is that for every year that passes, you could write 1 year, but hopefully if you say for every year, you mean it's 1 year. For every year that passes, the light clarity has tended to go down by 0.28 meters. Have I lost anyone on interpreting the slope? And do you think you're going to be responsible to interpret the slope? Absolutely. Okay, slope's very important. Okay, this is important. By the way, is that a good thing with Lake Tahoe? Those that live in Lake Tahoe, you should all know that. Is it good that for every year that passes, light clarity has tended to go down by 0.28 meters? Do we want that to keep happening and happening?
No.
No, that would be a complete disaster in Tahoe. And if you don't live in Tahoe, just trust me. If you live in Tahoe, you better know that. Okay, so that'd be a complete disaster. Any questions on that? Okay, so how about the y-intercept? Again, the y-intercept, first thing was, I don't have it memorized, it's in here somewhere. About, we'll go 48. Probably good enough. So the y-intercept was 48. Okay, so that's just what it is. Any questions so far? Okay, now hopefully you remember from your basic algebra that the y-intercept is the value of y when x is 0. Well, when x is 0, that was the year 1900 in this case, because this is how many years after 1900? And 0 years after 1900, hopefully you know, is 1900. And that's like nowhere in the vicinity of the data that was collected. And it's probably not very helpful. Does that make sense? So since 0 is nowhere near the data values, which start at 68, the y-intercept is not very useful. Okay. If it was kind of close to the data values, then you would say that your best prediction for what the lake clarity was in the year 1900 is 48 meters, because that's our y-intercept, because you have 0, 48. But in this case, it really doesn't make any sense. Any questions on that? There's a lot of reasons why the y-intercept will be useful or won't be useful. If it's nowhere near any of the data values, it's not useful. If it makes no sense, it's not useful. So for example, if we had a y-intercept of 3 million, that would make no sense for Lake Tahoe. There's no chance of ever seeing 3 million meters down in Lake Tahoe, since Lake Tahoe is not that deep. It's deep, but it's not even close to 3 million meters. Does that make sense? So the y-intercept, if 0 doesn't make any sense, or if the y-intercept number doesn't make any sense for the y value, the y-intercept's not useful. And also if 0 is nowhere close to any of these values, nowhere in the vicinity, then it's also not useful. Any questions on that so far? Okay, so next is, what's the best prediction for the lake clarity today? Okay. So just a hint. What is today? Y'all better know what year we're in.
2023.
2023. How many years is that after 1900? It's not hard. What's 2023 minus 1900? That's a hint.
123.
Yeah, 123, because from 1900 to 2000 is 100, and then another 23 years, so 123. Okay, so that's the same thing as saying, what is y of 123? And that is equal to, if you remember and I'll use this guy, just a minute. I think it's best to copy and paste. So I'm going to copy that sucker. Oops, wrong one, that one. Paste it in. And then x is 123. Any questions on that? And I'm going to go times. And the reason I did that way I can drop it in. I'll just drop it in here. And it gave me 13.79. Any questions on that? By the way, would we be okay if our lake clarity was 13.79 right now? Yeah, that would be horrible. Okay. Lake clarity would be awful. We'd have this muddy looking lake. Okay, so that would be horrible. So the best prediction for lake clarity today, based on the data, is 13.79 meters. Any questions on that? Okay, and that's if between the year 2000 and today, if the trend kept going. Does that make sense? Okay, so I'll talk about that in a little bit, but I want to talk about a couple more things first. Now we want to interpret R squared. So R squared was about 0.84. I'm going to go 2 decimals. 2 decimals is usually what you're going to want to do. And I'll explain that a little bit because then you can turn to a percent. So 84%. All right, so if we take a look, let's look at the picture again. We look at the data and we kind of ignore the year. We just look at the meters. You can see it's varying all the way from like 18 meters to maybe 30, maybe 32 meters. Do you see that? That's a lot of variation between 18 and 32. Do you see that? Okay, so if we ignore the dates, then these points are going to be all over the place between 18 and 32. On the other hand, if we kind of focused on little clusters all within maybe a few years, then you'll see like this little cluster, it varies a little bit, but a lot less than between 18 and 32. Do you see that? And if I go over here, for example, we get a little variation, but a lot less than what we varied between 18 and 32. Okay, and pretty much anywhere you go, you can have a lot less variation in your number of meters of clarity. Do you see that? Okay, so what that says is that if we can just focus on kind of a year or two, then the variation is decreased dramatically. Do you see that? Can you visualize that happening? Instead of being between 18 and 32, okay, and if you look at the standard deviation, we can get more fancy. You have a very big standard deviation. If we just looked at the meters, just ignoring the year, but if we just looked at little clusters near a year, the standard deviation is not very big. It might be just a couple. But if you looked at all the years, the standard deviation would be like 6 or so. Maybe 7. Be a much higher standard deviation. So what R squared does is it gives you that percent decrease in the variation. So there was a big decrease in the variation if you only look at clusters around one of the years, and that decrease was about 84% decrease in variation. So now we can write down there is a large variation in depth of clarity if we look at all years. But if we just focus on nearby years, then that variation on average tends to decrease, or just decreases, by 84%. Any questions on that so far? Okay, so sometimes you'll say the variation, that there's a lot of variation in the depth of clarity, but 84% of that variation can be explained. Sometimes they'll use the words explained by year. It's a little confusing, but that's what they'll often say. You'll often read that, is that the year will explain 84%, which means that if you just kind of look at the year and not worry about far away years, then 84%. And then the rest of it, the 16%, is explained by other things. Anyone know what other things, and this is not a math question, might explain the variation also in Tahoe? And here's a hint. My guess is this year, 2023, we're going to have a very low depth of clarity. And it's not because I like polluted the lake badly. I didn't do that. But any guess on anyone know? And this is not a math question. This is a science question. Come on, what's happening this year? Exceptionally large number of. This is, everyone should know, even if you don't live in Tahoe. Maybe if you lived in Europe or something, you may not know, but big in the news. Oh. Snow, yeah. We've had huge amounts of snow this year. And it turns out that if you have a lot of snow, what's going to happen is that snow is going to melt, even though it feels like it's never melting, but it's going to melt. And that when it melts, it's going to push down a lot of soil and other stuff into the lake. So 84% of the variation is kind of by year. The other 16% is explained by other things, such as how much snow you got in the wintertime. Any questions on that? Okay. So just a note, I kind of made a template. Another way of looking at it is the variable y has a standard deviation that can be quite large. You can use variation or standard deviation. They mean basically the same idea. But if we only focus on y values that correspond to a fixed value of x, so that means we only look at that year and nearby that year, then the standard deviation or variation is decreased by that percent. This is kind of a template if you like templates. But this is the example basically using that template. Any questions on R squared? It's pretty deep. It's more than just squaring a number. There's a lot going on here. Okay. By the way, little history. As I mentioned, the president understood statistics. And by the way, my student was there with him when this presentation was happening. Any guess on what she was doing? Serving him lunch. Because he was at it was the North Shore actually, and I forget which casino. It probably doesn't even exist anymore. He was one of the big casinos, you know, where they had a big room, and she served him lunch. It was my statistics student, and she got to see this actually happen. So it's kind of cool. If you ever have that, let me know. It'd be cool. I can tell people that my student did this. So my student actually got to see this actually happen, and she told me what the president did, along with the senators, by the way. And based on, you know, like guessing that the lake clarity is going to be terrible, you know, in the future. Any guess on what the president did and the Congress? They passed a law, a bill, and they put in, I think, over $100 million to deal with it. And there was a huge amount of work done to first research why the lake clarity was getting worse, and then come up with ways of fixing it and making it so it doesn't keep getting worse. Interesting. Okay, and that's the truth, by the way. It really happened. And I think the law, from what I read, is expiring now, and Congress has just brought up a new law to bring back the money. So our lake doesn't die. So let's hope it happens. I actually got an email this morning. Isn't that weird? Just coincidentally from our congressperson. You know, not just like personally to me, it was just his, you know, whatever, weekly email that he sends to all the people who sign up and talked about the law. Okay, so it's a big deal. So just some very important things to avoid. Never use the word cause. And something you may not have ever thought about, it's an English thing, not a math thing. The word because is just a variation of the word cause. I don't know if you thought about that, but that's what the word because is. It means caused by. So don't use because either. Other is don't use if, da, 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 then it will, because that's the same thing as cause also. So better words to use are tendency of or tends to. That's a good word. Or predicted is a good word. But stay away from cause. There are many things that you can get a correlation for, but you don't get causation. So for example, if you looked at the number of gray hairs a person has and how old they are, do you think there's a correlation? Do you think that people with a lot more gray hairs tend to be older than people with fewer gray hairs? Yeah. When you're little, you don't have gray hair, right? When you're young. Now, when you get older, you get gray hair, okay? Although if you get really old, maybe you don't have any hair, so you have no gray hairs, but I'm just going to not go there. But does that mean that if you dye your hair gray, it's going to make you old? Definitely not, okay? Because age really has nothing to do with how much gray hair you have. Do you see? Age in this case causes gray hair. Gray hair doesn't cause age. So sometimes one causes the other. Sometimes neither cause. Sometimes something else causes both of them. And that can happen too. Okay. There's all kinds of different things that could happen. So just avoid cause. So the way to establish cause, this is going to sound a little weird, is science. So for example, they have looked at the carbon dioxide in the atmosphere and the average global temperature. And they found a correlation. Okay, and they did this a while ago. Okay, now by saying there's a correlation between the amount of carbon dioxide in the atmosphere and the global temperature, does that say that carbon dioxide has caused our temperature to go up on average? Okay, and the answer is no. It doesn't say it. It doesn't mean it's not a cause, but you don't get it from statistics. So what happens is you get a collaboration between statisticians and scientists. And what happened is when the statisticians saw that there was a correlation, a very strong correlation between the amount of carbon dioxide and the global temperature, the next step is see if there's a cause. It might not be a cause. And the way you saw it was a cause is you talk to atmospheric scientists and chemists. And then you look for chemistry. And you see carbon dioxide, what is it doing in the atmosphere? And then the idea is you have this big red flag, but then that there could be a cause, but only could be. You don't know if there is. Do you see? Because regression analysis doesn't tell you there's a cause. So then you work with the chemists and the atmospheric scientists, and they do chemistry. And then they show that this carbon dioxide in the atmosphere, then they can show that if you have a lot of carbon dioxide, it's actually going to reflect, heat, basically. I'm kind of being simplistic, but it's going to reflect heat. And you do the science. And the science shows that it actually happens. Do you see? But the statistics tells the scientists that, hey, this might be something you might want to look at. Do you see? So the only way to do cause is with collaboration. And the collaboration is the science and the statistics. Does that make sense? Okay, so be careful about using cause or because just from statistics. You can't do that. You need collaboration. Okay, so if all you know is a r squared, that's not going to give you cause. Doesn't mean there isn't cause. It just means that you can't say there's cause from only that information. Any questions on that error? Okay. Another one, and I watch this in a psychology class. Every morning I watch a class, and I watched a psychology class. And they found out there was a correlation between the amount of times that a child is beaten by their parent and the probability of them ending up in jail when they become an adult. So does that say that being beaten by your parent causes the someone going to jail? Okay, and the answer is you can't say that. Okay, it means that you have a red flag, but it doesn't mean you can say cause just from correlation. Do you see? Okay, it gets really hard because maybe and this is what the professor said, not me, is that maybe the parents beating up their child because the child's a bad kid, getting into too much trouble, and they have to hit him once in a while. Okay, we don't know that, but that could be a cause too. Do you see that? And that might, so it may have nothing to, so the beating up may not have caused them to go to jail. Maybe them being a bad kid, a violent kid when they're young, caused them to get beaten up a lot. Okay, and those are the kind of things you have to do a lot more research to find out. Statistics isn't enough. Do you see? To show causation. But you can find correlation. That you can do. Okay. Just to note, the hypothesis test, which I showed you on the computer program, the calculator, and that is H naught is rho equals 0, H1 rho not equal to 0. Okay, because we want to show that there is a correlation. If there's a correlation, then the correlation is not 0. 0 means no correlation, by the way. Any questions? The good news is this is always what you're going to use for any question I ask. Okay, so you don't have to even do other things. It's always this letter, rho. Okay, it's not a P, by the way. RHO is how you spell it, by the way, if you're wondering. It's not ROE, it's RHO. And that's how you spell it in English. The way you spell it in Greek is right here. It's this letter. That's how you spell it in Greek. Okay, and we got a p-value of very, very close to 0. Okay, so this should be something that all of you already have down. If the p-value is very close to 0, what's the conclusion in general?
That there's statistically significant evidence.
Yeah, there's statistically significant evidence. Basically say H1 is true. And H1 is true in this case means, this one, means there is a correlation. So there is, and I'm going to write strong because it's really small. You never say strong unless it's really small, like less than 0.01, really small. And this is less than 0.01. Strong, statistically significant evidence to conclude that there is a correlation, and not a strong correlation, just correlation, between the year and the light clarity. It wants an is. Okay. Any questions at all on, let me make this bigger so you can see it better. Any questions at all on this? Okay, so just a note, I figured I should tell you the result. As I mentioned, fortunately, our president understood what this meant. After the presentation, the president was like, I have no idea what you just said. The president said, yeah, I take statistics and I get a little science and I understand. And that's a good thing. So now we can look at newest data. So notice that, up until here, right here, when there was basically nothing done to help before the bill passed and before the president made that decision. And then what happened afterwards? So if you look between here and here, so basically from the year 2000 to the year 2020, what's happening with lake clarity now?
It's getting a little clearer.
Yeah, I'm not even sure if it's clearer, but it's not getting worse.
Yeah.
At this point, there's I don't see any correlation, right? These points are kind of all over the place. Do you see? It's not clearly going up or down. Do you see that? It's just kind of flattish. Okay, we're not going back down here, but at least it's flattish. At least they've taken this horrible trend and stopped the trend. And they did that because of all this work that happened. Do you see how that works? Okay. And by the way, if you look at some of these years, like this year right here, you've been in Tahoe long enough, 2011, that was our last big, huge storm year. And guess what? We're at the next big, huge storm year. So it goes up and down and up and down. So after that, it got really bad because we had the big storm and then lots of flooding and stuff, and that made the lake worse. And then we had the drought. Drought was a good thing for the lake. Lake clarity got better. Up is, better, it turns out. And I'm sorry, down is better in this case. Yeah. So you have drought, and so it's weather stuff more than years. That's what's going on. Okay. Any questions on this example? So the correlation, what would your guess be what the correlation might be, say, between the year 2000 and the year 2020? What do you think rho might be? Remember, we found it was like 0.9 something, 0.91 was R, sorry. R was negative 0.91 in the pre Big Bill years. But in the post Big Bill years, what do you think R might be? The hint is it won't be negative 0.91 anymore. Any thoughts? What number do you think it might be? Looking at this data now.
0.5.
Okay, it could be 0.5. I would probably say clarity is not getting better. That means it's getting a little better.
Okay.
Remember, this is an upside down graph, right?
Yeah.
Okay, so clarity is not getting better. It's still a little bit worse. So it's probably still negative. Do you see? But now it might be more like negative, maybe 0.3. Yeah, more like negative 0.3. So it's a little bit worse, but not that much worse. Do you see? So it's pretty close to 0. Any questions on kind of eyeballing? And you can get all these numbers. I think I'm not going to do it, but I actually put all the numbers in. And you could do it if you want. Okay. Any questions on that? Okay, let's do another example. Okay, so unlike the one I just did with the lake and all that, those were real numbers, UC Davis and all that. What I'm about to show you, I just made up. So the data below show the results of a study of 9 community colleges done that looked at the percentage of students at the community college who received financial aid and the percent who were business majors. Okay. conduct a hypothesis test for the correlation, and perform a full regression analysis. So here's financial aid. And I'm going to go like this. I'm going to go down here. I'm going to hit new plot. And what that does, it just erases everything. You can hit the refresh button and that'll do it too. And I'll paste those X values in. And then let's paste the business major, which is the Y values. Okay. It turns out, by the way, if you switch which is X and which is Y, the correlation doesn't change. But the equation of the line changes. Okay. I'm not going to get into the math of that, but you can trust me on that. Okay. The correlation doesn't change. H naught, the p value won't change, but the correlation won't, but the equation of the line changes. Okay. And now if I hit new plot. Oh, sorry. I made a mistake. I don't want new plot. I want plot points. One more time. Let's get those back in. Fortunately, if you have the numbers separated by commas to start with, it's really quick. Otherwise, you got to type them in. And I'm going to hit plot points. So take a look. Is there a correlation? Does it look like it? Okay, it looks like it to me. If you go from left to right, it looks like it's going down. Okay, is it perfect? No. Perfect. If it's a perfect negative correlation, then R would be -1. If it was a perfect positive correlation, R would be 1. Just to let you know that. So it's not going to be, a -1, but it's going to be negative something. Okay, so if we go and look, we go ahead and you can see that here we have our slope and y-intercept, or y-intercept and slope. We have our R, we have our R squared, kind of similar R and R squared. Again, I just want to kind of show you another example. Here are p-values. It's a little bigger, but still small. So that means you get to reject a null hypothesis. There is a correlation between and let me remind you what it was, between the percent of financial aid students and the percent of business majors at a college. Any questions on that? Okay. Does the y-intercept make any sense? Okay, in this case, the numbers are all over the place. 20 to 72. 0 is not that far from 20. So that's not too bad. But if you look at the equation, can you have 37% business majors at a college? Can that happen? Yeah, that's possible. Nothing wrong with that. If it was 120%, you should worry. Do you see that? 37% is fine. Okay, that's no problem. Can you have no financial aid? Yeah, it would probably be one of those like really rich colleges where every student is rich and they don't get financial aid. So you can have it. There aren't too many of those, but they could have one. So what you would say is that your best prediction for a college that doesn't have any financial aid students, right? 0 means no financial aid students, is that 37% of those students will be business majors. Any questions on that interpretation? Any questions on that? The slope is about -0.5. So what that tells you is that for every increase of 1% in financial aid recipients, colleges tend to have a decrease in 0.5% in business majors. Okay, any questions on that? Okay, I'll let you know I made these numbers up, so This data could be found, and there may be a correlation, but I did make the numbers up. Okay, any questions on that? Okay, R is negative 0.9192, so that means you have a pretty strong correlation. Okay, typically like over 0.8 or so, you'll say it's strong. Usually between like 0.6 or so or 0.8, you'll say it's a weak correlation. And then below that, there's very little correlation. There's no like exact number at which you call strong or weak, but definitely this one's strong. This is 92%, 0.92, negative 0.92. Okay, R squared is 84. So that would say that there's a pretty large variation in the percentage of business majors from college to college. But if you only look at colleges that have the same percent financial aid students, then that variation is going to be reduced by about 84% on average. Any questions on that? Okay, did that help? Kind of seeing one more example like that? Because again, I could do example after example after example. I never know how many to give you. But I don't want to put you in pain. Let's see. Okay, so let's look at this one. This one I already have done all the work, all the calculation work for you. So suppose the equation of the regression line that models the relationship between the amount of time X in hours a person practiced shooting free throws in basketball, by the way, and the percent of successful free throws, Y, is given by Y equals 140 plus 0.4X. Correlation is, let's say R is 0.5. Okay, how do I find R squared? It's not a trick question, it's supposed to be easy.
By squaring R?
Yeah, just square R, 0.85 squared. So let's pop this in, 0.85 squared. And that is about 0.72. So R squared equals 0.72. I'll just do this to make it quicker. Or 72%. Any questions on that? So maybe I'll type this one out. So what we can say, let's do the following. So we can say is that there is a large variation and again, the Y coordinate is the free throw success. So in the percent of successful free throws. Okay, and this is for like many people. But if we look at only people who all have the same number of hours of practice, then that percent on average, actually the right percent variation, on average tends to decrease by 72%. Okay, any questions on that? Okay, use a regression line to predict the successful free throw percent for a person who has practiced for 40 hours. So this is actually easy if you know what to do. All you do is take this and put in 40. So I'm going to copy it, pop it in Google Calculator, take the X, turn it into a 40. And you get 156. Just a minute. Oh, you know what? This 140, I think, is a mistake. I copied and pasted it from before. I think there was an error there. That should be how it got 140. Let's go 0.140. Let's go 0.4x, 0.04x. Otherwise, this doesn't make any sense at all. Oh no, I guess it, let's see. Yeah, let's do that. Sorry about that. And then we get 1.7. That still is, I think I'm off by one. Trying to remember how I had this originally. I think it was, oh, it's percent. So 14.0. Is that right? No. Let's try. My copy and paste really didn't work because you can't have 140%, but we could pretend. So sorry about that. There was an error in my copy and paste. I don't remember what the original was. I had it somewhere. Let's see if, yeah, I don't have it anymore. But you get the idea? Okay. And that's the idea. So let me jump to the secret word. Secret word is variation. And that's because when you're interpreting R squared, you say there's a large variation in that Y variable if you don't even look at X. But if you focus on a specific value of X, then that variation is going to be decreased by R squared percent as a percent. So that's why variation is their secret word. So just note, regression analysis is used all the time. It's definitely in the top like 3 most important things in statistics when it comes to uses. Okay, it's used a lot because you want to find out if as one thing goes up, does the other tend to go up, and by how much? How much can you predict? Or as one goes down, does the other go down? You want to find out, is there a correlation for every field? Pretty much every field. Any questions on that? Okay, and you know, whatever it is, business or psychology or sociology or archaeology, all this stuff uses it. And I use it all the time in trying to understand the world. Any questions about anything? I think I'm going to call it a day. It's 7:30. I told you it's going to be a little shorter than usual, but not too much. And just remind you, next week will be on Tuesday. Tuesday at lunch will be the last one. And also not that hard because it's just one chapter and it's an easier chapter, actually. So it'll be your last one. And I want to mention one more thing before I drop the recording. Tomorrow, I have a meeting that goes till 4 o'clock that I can't get out of. I'm on a hiring committee and I can't just not be there. So my office hours are going to be 1 hour later. So they'll be 4 o'clock instead of 3 o'clock. So normally they're at 3 o'clock on Tuesdays, but tomorrow they're going to be 4 o'clock. So if you try to zoom in with me at 3 o'clock, I won't be there. Okay, or come to my office if you happen to come to the college. But at 4 o'clock it will. And then tomorrow is the most important holiday of the year. To me. What's the holiday? It's a special holiday where not only is it a holiday like tomorrow, but there's actually a moment in time where it's even more special. And that's at 1:59 and a little more than 26 seconds after that.
Pi Day?
Yeah, Pi Day, 3.1415926. It keeps going and going and going forever. Yeah, so tomorrow's Pi Day. So definitely have a great Pi Day tomorrow. Maybe eat some pie. And I think I'm gonna drop the recording, but definitely enjoy Pi Day, that's for sure. So let me stop the recording.